In this video, we're given a configuration of point charges. All four of these point charges are positive and they have a value of 0.5 microcoulombs. The point charges sit at the corners of a square of side length 1 meter. And we're going to answer several questions about this. In part A, we want to explain why the electric field must be 0 at the center of this configuration. So when we go to the center of the configuration, our electric field contributions come from 4 different places. We simply add the contributions from each of these point charges. And what I mean by adding them is they add vectorially. So if I call this charge number 1, its field contribution points down and to the right, and I could call that E1. If this is charge 2, its field contribution points down and to the left, away from that positive charge, that's E2, and so on. Now the magnitudes of all those electric fields are exactly the same because we have exactly the same distance from the same magnitude charge in every one of these cases. And I can see, for example, that E4 added to E1 results in a vector of length 0 because I'm adding 2 vectors head to tail that have the same length but opposite directions. In other words, these just cancel out. And the same is true for E2 and E3. So the resultant vector sum for these 4 vectors is simply 0. So I could say our official answer is that opposing electric field contributions cancel by symmetry. Now in part B, we want to find the electric potential at the center, and this is not going to be 0. Every one of these charges contributes a positive contribution to the total electric potential at that center. And what we need to do to find the contribution from each of these charges is we need the distance between the center of this square and one of the corners. And we have to do a little geometry to work that out. So here's a right triangle. And I can see the lengths of the legs for this right triangle are 0.5 meter each. So I can use the Pythagorean theorem to get the hypotenuse. I'm going to call that R in this picture. And once we have that, we can compute the potential contribution for each of these charges. So R is the square root of the sum of the squares of the side lengths. And we can keep this in exact form. When I take 1/2 and square it, I get 1/4. And so what I'm looking at here is the square root of 1/4 plus 1/4, which is the square root of 1/2, which you might prefer to rationalize as root 2 over 2, though it's not really necessary for doing the calculation. So then I get the potential contribution just from one of these charges. And by symmetry, what we're going to do at the end is just quadruple the result. And I normally write the potential contribution of a point charge as kq over r, where k is 8.99 times 10 to the 9th Newton meter squared per coulomb squared. So we'll plug the numbers in here. There's k. Remember, micro means 10 to the negative 6. So my charge magnitude is 0.5 times 10 to the negative 6 coulombs. And then my r is root 2 over 2. And when we run the numbers on this, we get about 6,357 volts for the potential contribution of just one of those charges. So the total potential at the center of this configuration is going to be 4 times that much. And if we round that to 3 significant digits, we get 25,400, in other words, 25.4 kilovolts. Now in part C, we're going to place an electron at the center of this configuration. So just a single electron there. And we're asked to compute the force on it. Well, there's not much to do in this part of the question because the force on an electric charge is given by the charge multiplied by the electric field at that point. And we've already shown the electric field vanishes. So the force vanishes as well, and the force experienced by this electron will be 0. In part D, we want to get the electric potential energy contribution obtained by placing an electron at the center of this configuration. So this is a negative charge that's close to a bunch of positive charges. This is going to be a negative potential energy contribution. And we're asked to express our answer in electron-volts. And actually, there's 2 ways of going about the solution here. And I'm going to do the long way first and then show the shortcut. So we have a formula for the potential energy between 2 point charges. And that's like this. It's a k q1 q2 over r, where that k is the same one we used in part B. So to get the potential energy contribution between this electron and one of the other charges, we start plugging the numbers in. And the charge on the electron is negative 1.6 times 10 to the negative 19 coulombs. That's where we're going to get our minus sign for the potential energy. And if it's interacting with just one of the charges for this calculation, that's 0.5 times 10 to the negative 6. And then our separation distance, again, was the square root 2 over 2. When we run the numbers on this, we get about 1.017, and it should be negative, times 10 to the negative 15 joules. Now there's also potential energy associated with the electron's interaction with each of the other 3 charges. So we need to quadruple this result. Into 3 sig figs, we get negative 4.07 times 10 to the negative 15 joules. Now we want to convert this to electron volts. And remember, an electron volt is the energy of an electron sitting at 1 volt potential, or I could say it's the amount of energy change of an electron moving through a 1 volt potential difference. And the energy change of an electron moving through 1 volt potential difference is given by its charge times the change in potential. As a magnitude, that's 1.6 times 10 to the negative 19 joules for each electron volt. And after doing the unit conversion, I end up with 25.4 kilo electron volts, so 25,400 electron volts. And this is a negative potential energy, so I'll pop my minus sign back in there. Now our alternative solution, basically the shortcut here, is to realize that in part B, because we already computed the electric potential at the center, and because I'm sticking an electron there, well, I know how many volts potential is at the center. And if I put an electron there, the energy is going to be the same number of electron volts. So this is our shortcut. I'm going to end up with 25.4 kilo electron volts with a minus sign out in front because it is a negative potential energy. And we're done with the problem. If you enjoyed this video or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.